Well, I'll start with telling you about Charles Babbage, who designed these things. And then I'll tell you what the machine does and how it does it. There's also a question about why it does it, and that'll be explained in the blackboard. So let's start with Mr. Babbage. He was born in 1790. So by the time he's an adult, we're in the midst of the Industrial Revolution. I like to call it the first Industrial Revolution because I think computers are a second one. Anyhow, this first Industrial Revolution is steam powered. Everything, textile mills, what have you, locomotives, everything powered by steam. There wasn't electric power yet. There were electric lights out, but not electric power. So steam becomes a metaphor for mechanization. Second topic, oh yes, Babbage. He was trained as a mathematician at Cambridge University. And in those days, mathematics was the closest you got to an education in science. The astronomers, the physicists, the chemists, the engineers, they were all amateurs. Good, talented, but not formally educated in their fields. Which might explain why Babbage didn't know jack about geometric optics, but that's a different story. I wanted to go into that. Okay, now, mathematical tables, these things that a lot of you dealt with and maybe suffered with, very important for almost all sorts of pursuits. But there was one pursuit which really interested the British government, navigation. Seafaring country, they were concerned that a ship might go on the rocks because of an error in the tables. Now, it never happened. The odds are really with the ship. But still, it was a constant worry because the tables were stinking full of errors. Why? Okay, 3 sources of error. You'll never guess the source in the middle, but I'll try, you guys. The first source, people are doing the arithmetic and people make mistakes. Third source, printer. He's setting individual pieces of type for each digit. He's bound to set some wrong.
All right.
What's in the middle? Yes? What error?
Reading something wrong, somebody's dyslexic, reading numbers the wrong way.
Well, you're getting close. You're getting close. Basically, these guys have been working on worksheets. They look like spreadsheets, okay? They can't hand that to a printer. He won't know what numbers to copy. They've got to transcribe those numbers, the final results, onto a sheet of paper they can hand to a printer, and they'll make some transcription errors if they're doing this all day long. So, the tables are lousy. Now, we get into the area of legend. History is full of legends you can't verify. Anyway, this legend is that there must have been a fly-in. In 1830, he's 40 years old, something like that. In 1830, he and an astronomer friend named John Herschel, you may have heard of Herschel, they're comparing 2 different versions of the same table, different editions. But they're calling off the values one after another. And when the 2 things they call out don't agree with each other, at least one table's wrong. At one point, Babbage has said to him, explain, I wish to God these tables had been executed by steam. 2 years later, he's figured out how to do it. Now, he has not invented the computer, not yet. What he has invented is a fancy, very fancy adding machine that can evaluate polynomials by nothing more than addition, which is a cute mathematical trick. And when he's evaluating, are things that look like this. They go up to the 7th power in x, which means you got to multiply x by itself 7 times. How do you do this with nothing but addition? I'll explain that at the blackboard later. It's a cute trick. And it's simple.
Good trick.
It's a very simple trick.
No.
And that's how modern multipliers work. It's a bunch of full adders and androids.
And no, it's not that you're multiplying by adding repetitively. You're doing very simple, a small number of additions. It's a different trick.
Because
It's
it's
called
a
the method of
relationship.
finite differences, which is a jaw-breaking name, and maybe it took some genius to think it up, but it's so simple it can be explained to anybody. It's really simple. Now, the point is that polynomials of that order can be very good approximations to other things over limited ranges. For a logarithm, which is a very, very smooth curve, the range isn't all that limited. This machine can calculate 3,000 seven-place polynomial, seven-place logarithms before we have to change the polynomial.
You're kidding.
I'm not kidding. I mean, this has been checked.
Well, then it's an amazing.
Well, it isn't the machine, it's the method. In other words, a given seventh ordering polynomial for seven-place logarithms is good for a range of 3,000 of them. Okay. Well, Babbage gets a grant of £17,000 from the British Treasury, which is the equivalent of some gazillions of bucks. He hires the best tool maker in the whole country, a man named Joseph Clement, and they start fabricating parts for this machine Babbage has designed. After 9 years, they have enough parts to make a working model. Now, it doesn't go to enough powers of x or have enough significant figures to be, it's just a model, to be really useful. Though Babbage kept it in his home and he would even demonstrate calculating logarithms. It's just not to the accuracy they would want in practice. The machine was about so big square, so high, weighs about 600 pounds. It lives in the British Science Museum, London Science Museum. Okay. Now, that's 9 years. On year 10, the whole project falls in a heap on the floor, collapses. It's kaput. It's done. The reason, Babbage, while very, very charming if you're his friend, you better not be his enemy. If you disagree with him, you become his enemy. It was his nature. Now, Clement has a very similar nature, and they wind up disagreeing with each other. The nature of the disagreement was very simple. Babbage wanted Clement to relocate his workshop closer to Babbage's home for better communication. This involves paying Clement some money. The disagreement is how much money. At that point, Babbage has this model in his home. It's his, I guess. But all the parts that Clement made after that point belong to Clement on British property. Well, he probably melts it over for scrap. And that's the end of this difference engine. Total end. Or Babbage, in his work designing that difference engine, has come to some grandiose ideas. He believes that he can make a machine now which will not only add and subtract. By the way, subtraction comes for free because you add what's called complements. I'll explain that later. But it will also multiply and therefore divide. Furthermore, it can store some numbers. It could obey instructions like take this number and multiply it by that number and put it there that come in on punched cards. Now, not these silly things, but the cards of the Jacquard loom, which were wooden things about so long and so wide, and each card was attached to the next card by strings, so it was a carpenter's cards which could be, stacked up. And finally, based on one of those stored values, it could jump ahead an arbitrary number of cards, which is equivalent to branching. So what he has conceptually invented is the computer. Nobody paid any attention, serious attention. It had no influence on this later reinvention of the computer, but everybody now agrees this man invented a computer. He called it the analytic engine. And he spent the rest of his life improving on it with drawings and text and notation. So, incidentally, there are some madmen in England who are talking about building it. It would be the size of a room or of a locomotive, you know, it's pretty fanciful. Anyhow, getting back to the main story, about 13 years into working on this analytic engine, he's changed his design ideas, even how he does addition. And he believes now he can make a difference engine with 1/3 the number of parts of the original engine. The original engine was going to have 25,000 parts. This engine has 8,000. And 4,000 are in this section, which does the actual calculation. And you can see there's a lot of repetition. And 4,000 are this smaller bit here, which will impress in the plaster of Paris a mold so that you can pour type metal in and get an entire page of a table untouched by human hands and free of error. And just to increase confidence, it'll also print on this tape. And there's an interesting thing about this method. If a number is correct, all numbers before that point also have to be correct. So that's the nature of the method. So anyway, he offers it to the British government, which says thanks but no thanks. Now we jump ahead to 1985. The London Science Museum hired a new curator of computing, a man named Doran Swade. And Doran is convinced that if Babbage had gotten a grant from the British government, he could have built that machine and it would have worked. And there were other experts who said, no way, because there was no mass production in England. Everything was sort of done by hand. And therefore the tolerances were pretty big. And they just said, with that kind of sloppy manufacture, the machine couldn't work. Doran decided the way to prove it was to build the machine. So he starts raising money. And funny things happened. I mean, there was one point when he needed 20,000 pounds in a hurry because of a contract with an external manufacturer, and he had to interrupt the Board of Trustees meeting of the museum with a scream when they were about to adjourn. He thought he'd be on the agenda. I need 20,000 pounds. The head, I think, of the ICL said, we'll give you 20,000 pounds. But the most entertaining thing in that chapter, it's mostly a biography of Babbage, but it does talk about how he raised money. The most entertaining thing to me was when he literally blackmailed 30,000 pounds out of IBM.
They don't give money up easy.
Anyhow, it was a threat of bad publicity. A threat that the publicity would be that IBM killed this project by not donating money. IBM wanted it to be called an IBM thing, you see. Well, anyway, they demonstrated it to the press on the 200th anniversary of Babbage's birth. So it was 1991. It took them 6 years to build it. And they only had enough money to build this much. So now we get back to some more legend because the details, I'm kind of half inventing them. But basically, as I understand it, Bill Gates sees this thing, and they figure he's a good touch for some money to build this. And he declines, but he puts them in touch with a man named Nathan Meyervold, who had been Babbage's chief technical officer. And Microsoft, what did I say? Oh, I'm sorry, Microsoft's chief technical officer. And Nathan, after a lot of exchange of email, makes them an offer they can't refuse. He says, I will pay for building one more of these and two of these because I want that machine in my living room. Which it turns out it's a bit of a museum. So anyhow, the machine gets built, another 6 years, and the chairman of the board of trustees of this museum, Mel Shostak, persuades him to lend it to us for 1 year. And on the spring of 2008, it arrives at our front door. It was in terrible condition, by the way, because nobody had experience shipping a thing like this. It weighs 5 tons. Now, it was built with provision for attaching diagonal braces, but still there was a lot of vibration on the airplane, and some of the screws that hold the damn frame together were found in the oil pan. And people didn't sort of realize the hazard of a slight misalignment of this machine. It turns out, let me put it this way, Babbage was a great mathematician, a great inventor, in certain respects a rotten engineer. Because the way this machine is timed, the very instant that one action ends, another action begins. There's no free time in between. So if it gets a little out of alignment, two parts of the machine may try to occupy the same space at the same time. And if it's a fragile part, it snaps. And in fact, there's a part called the carry lever. And the carry lever is very fragile. There's a picture here where it's not all that visible, but it's the thing at the bottom. You can see a round part and then a long arm coming out. And that long arm is brazed to the cylindrical part. The rest of it is one piece. And those just snap off if you look at it too hard. The first time they cranked this machine, 6 of them broke. And they cost, I've heard various figures between $600 and $1,500 to make one. Well, at a point when we ran out of spare carry levers, Nathan said, it's not a problem. There's a company that I just bought which will make them. And that company managed, I love to see the machine that does it. It made them out of one solid piece of bronze. So they're much stronger than the originals. Now, I will say one thing about making this machine, Doran Swade, because he wanted to prove this point, that Babbage could have done it. Well, first of all, they used that model in the museum, that model known as the beautiful fragment, to decide what parts should be steel, what parts cast iron, what parts bronze. Second place, when contracts were let out to make these parts, they were made oversized and finished by hand. So the tolerances are what Babbage could have achieved. The machine is sloppy, as it would have been in Babbage's time. So that was the proof that Babbage could have made it work, that this machine works after fashion. Okay. Now, I'll start telling you what the machine does, how it works, and so on. There's a shaft here, the main shaft. One turn of this main shaft produces the next result in this column. And you read the numbers from top to bottom. So the least significant figure is at the bottom. And by the way, we've isolated the bottom 4 to tell the value of x. And above that is the remaining digits of the 31 are the value of the polynomial. Okay. Now there are 7 columns. We'll number them 0, 1, 2, 3, 4, 5, 6, and 7. Oh, I'll say one other thing. No human being would be strong enough to turn this main shaft, so there's a 4-to-1 reduction here. Babbage would have found that out. But in the interest of being authentic, the crank can actually be mounted on the main shaft. So if ever Superman arrives, then you see if we may try him out. Now, what happens is, the cycle, which is one turn of the shaft, which produces one answer, is divided into 2 half cycles. In the first half cycle, the number in column 7, which never changes, is added to the number in column 6. Simultaneously, the number in column 5 is added to column 4. The number in 3 is added to 2, and the number in 2 is added to 6 is added to 5, 4 is added, 7 is added to 6, 5 is added to 4. Odd numbers are added to even numbers, and finally 1 is added to 0. In the second half cycle, the evens are added to the odds. So column 6's number is added to column 5, and so on down. And that's all it does. So now here's how it adds. gets a little more complicated. Let's consider these two columns that I have my hands on. In between these two columns is a column in the middle. And people behind me can see that that column is about, the gears in that column are about so thick. See them? About a half-inch thick. On the other side of these gears, they're only about an eighth of an inch thick, which you guys can see. Okay? Now, first thing that happens, a rod inside these unnumbered columns descends a little bit. And that rod has fingers at the level of every wheel. 4 fingers, because the numbers go around 4 times. And inside the wheel there are 4 bumps.
So it's looking at the number.
And that rod rotates. And what it does is it sets each individual wheel to 0. There's an index mark. So if a wheel was showing 9, it would be moving all the way around. If it's showing 0, it wouldn't move at all. And because it's connected to this gear, which is connected to these teeth, the number in each one of these wheels is added to the number in this wheel. What have I left out? Carry, right? If one of these wheels during that addition hits 0 or goes beyond, we got to add 1 to the wheel above. And if that makes that one hit 0, then so on. Okay? Well, I'll explain that in a moment by waving my hands. But first, I got to tell you the other step. There are 2 steps that take place at once: taking care of the carry and restoring a number here. Because everything here is 0 now. We've lost the data. Now here's the magic. This whole column goes up. It goes up just enough so these thin gears disengage. But the thick gear stays engaged. Now if these are returned to their original position, that restores the number here. And while all that is going on with these 2 columns, the sectors on the outside are in a 3rd position, where even the thin gear is disengaged, because these things have to be free to turn. They can't be tied up to the ones on the outside. So that's addition, except for carrying. Now I'll try to explain carrying by waving my hands. The carry lever, there was that long thing. Okay, and you saw those spiraling, beautiful spiraling things going in opposite directions. They will miss that arm when that arm is in its normal position. But every one of these wheels has 4 sharp bumps on the outside. I'm touching one right now. And when that wheel goes through 0, or hits 0, it hits a part of that carry lever, and it moves it 1 little notch to a position saying, I need a carry. And in that new position, the spiraling thing can whack it. And when it whacks it, it moves it further. And then a part at the upper level adds 1 to the wheel above. So now if you had added 1 to a bunch of 9s, the carry could triple up the machine. And that's the best I can do with the carry. So that's that. Now there's one last thing for you to look at. You want to look at these columns, sector columns, moving up 3 positions. And you'll also notice that the odd ones and the even ones don't move at the same time. Because remember, the machine was first dealing with adding odds, and then the next half cycle it adds evens. So those 2 sets of sectors behave differently. Now, finally, the thing which makes all the noise. See this? My rundown is there's a sharp edge here on the right, relatively sharp. It goes the whole length of the machine. And after addition, remember, these things are sloppy. That thing comes slamming into the teeth, and it digitizes, actually makes accurate the position of the wheel. And one of the ways this machine can jam is if somehow the lock hits a tooth dead center. Then we're dead. We have to undo a screw and free up that lock. So now, I'll make it a few cycles. and you'll get to see the things I talked about. Now, one other thing, every full cycle this comes up, and if we put ink on the roller it would print. We don't. It would be a big cleanup job. And similar things to these. Here is the wheel with the typefaces. Well, there's a similar thing where it would come down and punch it to the cluster.
It's all done there. I can see it.
No, you can't see it actually.
Can't see that?
It's better.
No, no,
But-
above it.
These are just counterweights.
No, no, not that. The actual teeth.
Oh,
Not this.
this is
This, I see this.
that is not.
That's not. No,
No,
the
that is
gear.
not.
The gear. I see.
The punch that comes down is really buried in the works. As a matter of fact, I think right now they're removed. And the motive power for moving this tray is the weight. And if he cranked down to the end of a column, his cranking would rewind this weight. And when it gets to an end of a page, a weight falls off some kind of a treadle, and somehow it manages to pull on this string, which goes the whole length of the machine. Here's the string. I'm told this is actually kept up. And it comes out to here, and it pulls on a clutch. So when they're at the end of a page, this crank will just spin. It won't calculate ahead until they put in a new tray and reset it. So that's all I want to tell you about. Oh, one other thing. The program, the thing which works everything, are these cams. Every one of these cams makes something move at the right time, which causes either a vertical motion or rotary motion. There are 2 cams for every motion. One pulls, one pushes. We don't have springs as cam followers. Okay,
That's
crank
okay.
away.
You got it.
And where's all these good things? Should we do a check or volunteer? Sure. Okay, X is 240, so. You want to volunteer? Okay, you can just. Here's a line 240, and I'm going to read off these digits. And you'll tell me whether that which is right. Half the time I read these wrong, though, so. 0, 0, 0, 0, 0, 3, 5, 9, 1, 5, 4, 2, 4. Whoops, 2, 5.
Yeah, thank you.
It's just sort of in between the two. 2, 5, 4, 1, 3, 6, 6, 2, 8, 2, 0, 1.
Yes.
Is that right?
I was watching too.
Now, I'll go to the blackboard and I'll try to tell you what this nonsense is all about.
Yeah.
Now, on this blackboard is an example of a polynomial. A very simple polynomial, x squared plus 1. And we have values of x here and values of the polynomial. Now, the important thing for the method to be valid is that these are equally spaced. They don't have to be integers. For that machine, they would be 1, 2, and 3 over in the 7th decimal place. So you got that. Okay. Now, if x is 0, x squared plus 1 is 1. If x is 1, x squared is 1, add 1, you get 2. If x is 2, x squared is 4, add 1, you get 5, and so on. So that's just a table of values. Now, what's called the first difference is the difference between two consecutive values of the polynomial. So we subtract 1 from 2, and we write it down here. We subtract 2 from 5, getting 3, we write it here. 5 from 10 is 5, and so on. First difference. For the second difference, do the same thing you did for the first difference. So, subtract 1 from 3, you get 2. Subtract 3 from 5, you get 2. Notice something? They are constant. The second difference is constant because the highest power is 2. Over here is a more complicated polynomial. It's just there for show because I won't really use it. But notice that the third difference is constant because the highest power is 3. Now, how many values do you have to calculate the hard way, the way we just did, to know the value of the second? If the highest power is 2, you're going to have to calculate 3 values because you needed 2 values to get this, and you need the third value to get this one, so you can do this subtraction. Now, if you know calculus, it's the second derivative.
Yeah, it's derivative. I know that.
That's cheap.
I
Okay.
know it's cheap.
Now, here's the magic. Let us just take these values, 2, 3, and 5, and write them down. 5, 2, 3. And I'll write down some zeros to get a total of 1, 2, 3, 4, 5, 6, 7. Now, I want you to pretend that machine is a little more stupid than the machine I described. Because I'm going to describe the way people would calculate. Suppose we didn't have this parallelism that I was so happy with. You know, that in the first half cycle, all the odds are added to evens. Let's just say the machine adds the 7th difference, the 7th column to the 6th column. And the next turn of the crank, it adds the 6th to the 5th. And the next turn, it adds the 5th to the 4th, and so on. I'm going to do that here by hand. So I'm pretending I've set up these columns in that machine. Now, since the first 4 are 0, they're never going to add anything to anything, so I can just forget them. Now, we're going to add the next column to the low column. So we're adding 3 to 2. So after the addition, what does it have? It has 5. Now we add this one to this one. After the addition, it has 10. That's the next value. Now we can do it again. We add 3 to 5, and we get 8. What?
I think you switched different one.
I switched something.
So it should be 5, 3, 2.
Oh, this should have been a 2.
Yeah.
Yeah, again, this should be a 2.
It should be a 2. So we get 7, and we add 10 to the 7, we get the 7, and so on.